Hey guys, it's me, Mr. Arias again. Here's our next installment on volume. It's the DISC method, and you can pretty much see right here in big bold capital letters it says it's on the AP exam, and yes, it is on the AP exam. Now, there's another section. I'm going to jump really quick just to touch on this. I'm going to jump to the shell method. Okay, we're not going to do the shell method this week. Reason being is, well, it's on your calendar for next week. But even when we do it, we're only going to do it just for a day because, to be honest with you, it's not really tested on the AP exam. All right, and the other reason is because you can actually find the volume of everything using the DISC method. And of course, for those of you that are ever going to move up higher in mathematics, well, to be honest with you, there's another way to find the volume of just about any object you can imagine using three-dimensional and triple integration, which essentially kind of makes the DISC method in a way kind of obsolete in a way, I guess you could say. Okay? But it's not necessarily obsolete. It still finds volume, but let's just say there's more advanced ways. But anyways, that's let's just do one step at a time. Okay. All right. So to find the volume of the disk, okay, of the disk method, also the washer method. Okay. So first, let's start off by finding the volume of a cylinder. And if we use basic geometry, okay, the volume of a cylinder is just pi r squared times its width. But if we start updating this with the calculus version of a disk, if we go to a disk, it's pi times the radius, and the radius is going to be measured right here by whatever the function is. I'm going to go over here. So here's the radius, which is now represented by a function called r of x, and then that's squared, and then its radius instead of w is now delta x. Okay, and that gives you the volume of a disk. Now, says adding the volumes of all the disks together. Well, what symbol tells us to do the summation of just about everything? Well, sigma. And so we're going to start with the first term, 1, and we're going to go all the way to the nth term of pi times r of xi squared times delta x. And if you remember, this is kind of very similar to the definition of a Riemann sum. Whenever you add up all the rectangles infinitely many times, that's similar to that definition, but it gives you area under the curve for the Riemann sum one. Okay, now it says to get the exact volume of the solid, you're basically going to do this, but you're going to do this infinitely many times. And what do you get? You get this equation. We're going to go ahead and jump straight to it, and it gives you this. From a to b times pi of r squared x dx. Okay, and so that gives you the volume about horizontal axis by disks. And whenever you do it vertically, it gives you pi from a to b, but this time it's in terms of y. So I'm going to try to fit a little y in here. And this is a function in terms of y. Okay? All right? Okay, and so that one gives you the one when the volume about a vertical axis. Okay. Now, before I jump into the other one, I want to go back here and just kind of explain where all this comes from before we go any farther. Okay, so what we're talking about is finding the volume of disks and washers. So this concept kind of comes from the section we just did over finding volume. Remember, we just talked about volume in the previous section, as volume is the integral from a to b with respect to whatever variable, dx, dy, dz, whatever it is you want. And you're finding you take the integral of the area function, right? You find the integral of the area and it gives you volume, right? Well, if we want to find the volume of a disk, well, we find the area and then we integrate, okay? And what's the area of the bottom part of the disk? Pi r squared. And so when you integrate that area, it gives you the volume, which is the entire cylinder. Now, if you want a visual aid, here it is, okay? So suppose you were rotating around this horizontal x-axis right here, okay? If you're rotating, this is essentially what the math is doing. It's rotating, and then it comes back around, and then it does that for every single point, and it comes back around, etc., etc. And then these tiny little pieces give you this one, and so eventually what you get is this kind of cone, kind of strange looking tornado cone disc kind of looking thing. Okay, and of course it's a three-dimensional object. Okay, and I hope that was a good visual aid. Normally when we do this in class, I actually have objects that are made by finding the volume using the disk method so people can use them. When we come back next week, I'll show you. So that way, hopefully that gives you a better visual aid. So now let's go on to this one. Now the next one that we're going to talk about is what's known as the washer method. Okay. Now for those of you, okay, well, if you have or have not ever done any kind of, I guess, work with tools or anything, you know that a washer normally has a circle inside, right? An empty circle, or what most people would call donuts, okay? Because everybody loves donuts. They're awesome, okay? And so basically this is how it works. The washer method basically comes from this concept. I'm going to start all over again. Suppose you have some circular object, right? And it gives you a disk modeled by some function f of x, right? And so when you integrate, let's say it gives you a disk, right? And let's fill this in, and it gives you this disk right here. So let's say you want to cut a piece out. You want a washer method, which is essentially what it is. You cut a piece out of it, and you would be left with what's known as a washer, donut, etc., etc. And this would be modeled by some other function g of x. And so you cut that piece out, okay? And so before I go into the formula, I'm going to kind of use some a basic concept. All right, when you were in geometry and you wanted to find out, I guess, the volume using basic equations, you would have a circle, and let's say it would have its width. Let's say its width was 3. Okay. And it had a certain radius, right? And so if you wanted the volume of the cylinder, you would do pi r squared times the width, or the height, which is 3, okay? And then let's say you wanted to cut a piece out of it. Well, you would cut a piece out of it right here. And so then what do you do to cut a piece out of it? You subtract the inner circle, okay? You subtract the inner circle. So this would be the big one. And then you would subtract the smaller one, okay? And the smaller one, of course, would have a smaller radius. And so that's where this whole concept of the washer method comes from. And it looks like this. Okay, you're going to do the big radius minus the smaller one. And that's when the axis are, on a horizontal axis, okay, when you're rotating about a horizontal axis. And then when you're doing it about a vertical axis, this will be from A to B, same thing, but this will be big R of y squared minus little r of y squared dy. Oh, my apologies, that's supposed to be an x, okay? All right. And so I hope maybe this will help you. This right here, the big R is supposed to represent the big circle, okay? And then the little one is supposed to represent the smaller one, okay? All right, and so that's essentially kind of what we just did a second ago. You find the volume of the big cylinder and you subtract the smaller one. Okay, I'm going to go back really quick to give you guys a hint on something, okay? Because I know that this question will come up a lot, and so here, let me just go ahead and answer this real quick. Okay, you see this example right here? And you see how the width of the rectangles are on the x-axis, okay? When the width of the rectangles are on the x-axis and you're rotating this way, okay, that's when you know you need to have an integral with respect to x, okay? That's when you have an integral with respect to x. Now, we're about to get to it here in a second, but when the width, here I'll use this one on the left as an example. When the width of the rectangles are on the y-axis and you're going to be rotating this way, okay, when you rotate this way, that's going to be an integral with respect to y when you do the washer method, disk and washer method, okay? And so let's go ahead and here's some notes right here for you guys, okay? All right, and let's go ahead and let's put it into practice. Okay, so let's go to this example. It says, find the volume of the solid formed by revolving the region bounded by the graphs of the given equations about the indicated axis. Okay, so here we go. We have this equation, y equals 9 minus x squared, which is your basic parabola. Okay, it has a negative slope and a y-intercept of 9. So I'm going to go ahead and put it right there. And has a negative slope of 1, so it should look something similar like this. And it'll make a shape like this. Okay? Now it says bounded by this, x equals 0 and y equals 0. So here's y equals 0, and here's x equals 0. All right? So there's the x-axis, y-axis. So it looks like we want this shape right here. All right? Now, I'm going to be honest with you. You can look at this two ways. You can say, oh, why isn't it the left side? Well, you know what? It doesn't matter which way you do it, whether you pick this left side right here, whether you pick this one, or the right side. When you do the math, you get exactly the same volume. So it really doesn't matter, okay, for this case. All right. So let's go ahead and let's practice. It says find the volume about the x-axis. Okay, so we are going to rotate in this direction. We're going to rotate the object in this direction. And if, for those of you guys that want a better visual aid, all right, think back to when we did Riemann sums. Remember that a Riemann sum takes widths of rectangles underneath the curve, right? And so look at these rectangles. I know my drawing's not perfect, but the width of each rectangle is on the x-axis. And if we would rotate that, look at what we would get. It would come back around, and then if we would rotate this one, it would come back around, and then we would get this strange little cone-looking thing right here. Okay, my apologies if my graph isn't perfect, okay? All right, and so we would get something that looks like that, but should look better, okay? And so since we're revolving around the x-axis and the widths of the rectangles are on the x-axis, that's dx. Remember that in order to find volume, we integrate the area. Well, what's the area of a circle? Pi r squared. So we need pi. And we need the limits, okay? We need the lower and upper limits. Remember that we talked about a long time ago that remember I said that this d whatever will be very, very important in future mathematics. And it is very important. And it'll be even more important in the future, okay? All right, so that tells me that my limits need to be with respect to x, okay? So my limits, my lower bound, if you look back here, the lower bound is 0. And what's the upper bound? Well, you need to find out when does this graph touch right here, the x-axis. So what you do is you're going to take this equation and make it equal to 0. Well, if we use some basic algebra, blah, 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 we get x equals plus and minus 3. Of course, we're doing the one in the first quadrant, so we want the positive 3. There it is. Okay, and now we want the radius. We want the radius of this circle. So what's the radius? It's this curve right here. Okay, it's this curve right here. So it's that curve. Okay, and so, all right, so what's going to give me that curve? Y equals 9 minus x squared. Okay, all right, and I'm going to touch on this because I know this question may come up. All right, remember we always do top minus bottom whenever we integrate with respect to x. We always do top minus bottom. Well, there is no bottom function right here. The bottom function is the x-axis itself, which if you did want to get, I guess, precise, there would be a minus 0 here. But we're not going to do that. We're just going to leave it as is. And don't forget to square it, because remember, in order to find the volume of a disk, we do pi r squared. And by the way, if you're wondering, where's the width of the disk coming from? Well, the width is represented by dx and these boundaries that we picked right here from 0 to 3, okay? And that is it, okay? Oh, my apologies. It actually says to find the volume. Okay. All right, so let's do that then. All right. Here, let me just clean this up. All right, let's find the actual volume. So this will be pi times the integral from 0 to 3, and of course that's a factor, so we're just going to FOIL. If you FOIL that, you should get x to the 4th minus 2 times 9 is 18x squared, 9 times 9 is 81 dx, and then if you integrate, you're going to get pi times x to the 5th over 5 minus 18x 3 over 3 plus 81x evaluated from 0 to 3. And by the way, don't forget, you're multiplying this whole thing by pi. Okay, and then what do you do after this? You just substitute in 3. And of course, if we substitute in our lower limit, it's going to be 0. So when we subtract it, we're basically subtracting nothing. So this will just be pi parentheses 3 to the 5th and 3 to the 5th over 5 minus 18 divided by 3 is 6. And 3 to the 3rd is 27, so that's 6 times 27 plus 3 times 81, which will be 243. Okay, and so then we combine all of this, all right, and we should get pi times 648 over 5. All right, and that's the volume of this object when you rotate it. Okay. By the way, a nice helpful tool when you guys do your homework for this is that when you look up your answers online using CalcChat, all right, I think if my memory serves me correct, Larson will leave his answer without multiplying by pi. He'll leave his answer like this. Okay. Now, if you want to, you can do this by hand, and to check to see if you're right, you can plug this in your calculator, integrate, and then at the very end multiply by pi to verify if your answer is correct. It'll be a helpful tool for you to see if you're on the right track. All right, so now let's go to part B. All right, and so this is the one part where it'll start becoming somewhat challenging for students, okay? And so I'm going to try to give you guys the best amount of hints that I can to help you along the way. Okay, so it's still the same shape, so I'm just going to go ahead and re-sketch it. There it is, okay? And so, and by the way, if you can hear that, they're still, I guess, building on the other side of this wall, okay? All right, so it says you're going to rotate about y equals -2. All right, and this is one of those things that just starts causing a whole lot of confusion. Reason being is because, well, actually here, let's focus on the basics. First, we're going to rotate, so we need, in order to find the volume, we need the area of a circle, so that's pi, and we're going to rotate this way. And so the widths of each rectangle are still, where are they? On the x-axis. So you need a dx here, which also means that your limits still need to be in terms of x, which is from 0 to 3. Okay? All right. And now what we're going to do is we're going to start finding the radius. Okay, this is where I guess you need to practice drawing your graphs. All right? Now, if you notice, if I do you guys see this blue right here? This blue dot right here? Okay. If I rotate this part around this axis, all right, look, if I rotate it, this is going to be the same also right here, right? And so what's happening is that when you rotate, what's happening inside of this shape? What's happening? What's forming inside? Like this empty hole-ish is forming inside, right? So what this is going to give us is the washer method, because it's essentially cutting out a piece inside of this shape. And if I fill in the rest, here I'm going to fill in the rest. I'm going to rotate this part. It's going to come back around, rotate this part, and then finally rotate this part. So you can see how we get this empty space right here in blue. We're getting this empty space right there, right? So that means that we're going to use the washer method. We have to do the big shape minus the small shape. So the big radius, now this may help you, well, this may help you, okay, I hope it does, okay. Remember that we would use big R squared, right? Big R squared represents the big or the larger radius. So this right here is your axis of rotation, right here. This in yellow is your axis of rotation. Which one is the farthest away from the axis of rotation? Which one has the largest radius? If you were to start right here, the one that has the largest radius is that right there, which is, guess what? The function itself, 9 minus x squared. So that's going to be my big R. Okay, so let's go ahead and let's fill that in. So that's pi 0 to 3. Okay, and I'm going to go ahead and plug it in, 9 minus x squared. Okay, now this is the part where people start getting a little confused, right? If I would just square this right now, let's say I just square this right now, right? That would give me, this right here would give me a cylinder that's completely filled in, right? It would give me a cylinder that's completely filled in with no empty holes, right? And so I have to cut it out, right? Well, remember that whenever we integrate with respect to dx, we do top minus bottom, right? Well, you notice that this shape right here stops right here at y equals 0, right? Okay, so I need to cut this piece out. This piece that's right here. I need to cut this piece out. Okay, and so we would subtract, right? So we would subtract. And so what is that function? Well, it's y equals -2. So if I plug that in, I get -2 squared, right? So that would be us cutting this piece out right here in the center. But there's one other little tidbit that we also can't forget. When you rotate this, since you are no longer rotating about y equals 0, okay, doesn't this part right here, doesn't this add to the radius? This distance right here is adding to the radius, right? So what does that say about big R? Shouldn't we be adding to this radius because it's getting larger? And what is it adding by? We're adding what to the radius? We're adding a factor of, guess what, 2, right? And so whenever we integrate with respect to x, we do top minus bottom. So what's the top function? 9 minus x squared. What's the bottom one? Y equals -2. So when we do, and I'm going to do it right here because it looks like I'm not going to have enough space. We do top minus bottom, right? And what's the bottom function? -2. And my apologies, I put an equal sign there. So that's minus a -2. And so what happens? A negative times a negative turns into positive, right? And then 2 plus 9 gives us 11. So that's going to be right here. So we get 11 minus x squared. And then there's our integral. That thing is going to give us the volume. Okay. And by the way, I know that this is probably the one part that's the most challenging. If it helps you, think of it this way. Because the axis of rotation got shifted downward, right? It added 2 units to the radius, right? So what did we need to do? We needed to add 2 units to 9 minus x squared, which gives us 11 minus x squared. So you can think of it that way, okay? Or you can just think of it as I just mentioned it. You do top minus bottom, which is 9 minus x squared minus the -2, and then that would give you this big radius, okay? All right, and so now let's do the math, okay? So here I'm going to erase some of this to give myself some space. And so this will be pi, the integral from 0 to 3. When you FOIL and distribute that, you should get, hold on. Yes, that should be x to the 4th minus 2 times a times b, which is going to be 22x squared plus 121. -2 squared is 4 minus 4 dx. And so this is going to be just pi 0 to 3 x to the 4th minus 22x squared plus 121 minus 4 is going to give us 117. And then we integrate. So this will be pi, the integral. Actually, you know what? Yeah, let's integrate. So this will be pi brackets. Oh, and by the way, I'm kind of aware that you may not have some space, so you may want to either write small or just do this on a separate sheet of paper. Okay? Sorry about that. So this is x to the 5th over 5 minus 22x to the 3rd over 3 plus this, evaluated from 0 to 3, and then now we're just going to plug in all of our variables. And so that's going to give us pi of 3 to the 5th over 5 minus 22 over 3 times 3 to the 3rd plus 117 times 3. And of course, I'm not going to do the second bottom limit because it's just 0 and it just cancels everything out. And so plug all of that in there. And here, I'm going to use a calculator because chances are this may be on your calculator portion. All right, if not, then we'll basically do some basic arithmetic. But you will have a calculator portion. So what is that? Pi times 3 to the 5th over 5 minus, let's see, this cancels out one of these, so that's 3 squared, which is 9. All right, and so I get 633.345. All right, and there you go. All right, let's go on to the next one. Let's go to part C. All right, so in part C, it says now you're going to rotate about the y-axis. So it's the same concept as before. All right, this is the part that gets students the most. It's the same shape. So same shape, you're still going to do the same thing. You're still going to do that right there. But now you're going to rotate about the y-axis. So the rectangles are sitting on the y-axis. So here are the widths of the rectangles. They're right here. Here are the widths. So when we rotate, all right, when we rotate, it's going to be doing this. It's going to be doing this. What do you know? It gives us, wow, what do you know? Very, very nice half of a football. Okay, that's nice. All right, so that's the y-axis. This is the x-axis. So because we're rotating around the y-axis, this will be with respect to y. And remember, of course, the Washer method is pi r squared, so we need a pi. All right, and we need, because this is dy, we need the limits in respect to y. Now, the bottom limit is still 0. Now, what's the upper limit? The upper limit is going to be 9. Okay, if you remember, if you plug in 0 into this equation right here, y equals 9 minus x squared, you'll get 9. So the upper limit is 9. And so now we want the big radius, right? We want the big radius. But remember, that's in terms of y, not in terms of x anymore. So what's going to go inside of there once you solve and do some algebra? You should get the square root of 9 minus y. And then we square it. Let's do some simplification, and here, let's do some math. Okay, and so you get this. All right, and now it's time to substitute. We get pi times 9 times 9 gives us 81. Then 9 squared is 81 over 2. And of course, minus big 0. Okay, I guess this time I won't leave it out. And of course, 81 minus 81 halves is just going to be another 81 halves. So that's just pi times 81 halves. And there you go. That's the volume of half this football. Okay, there you go. All right, let's go to part D now. So part D is actually very similar to part B. It's very, very similar. So here it is again. Now we're going to rotate about x equals negative 2. So we're going to be rotating around this axis. So you're going to be doing this, right? It's going to come back around, right? And you're going to get this shape right here. And it's going to create this empty hole in the center right here. It's going to give you like this empty hole, okay? Which is actually kind of like a washer or nut, I guess you could say, okay? All right, same concept. So let's go ahead and let's set it up. We're revolving around the y-axis, so I need a dy. The limits are still going to be the same, so it's 0 to 9, okay? And so, oh, by the way, so at the beginning of the notes, it said that this is on the AP exam, and it is. All right, and many times they'll ask you to just write the integral that gives a volume. All right, so now more than ever, it is very, very important to label what d, dy, dx is. The limits are very important, and it's also very important to not forget pi. All right, and believe it or not, you really do get credit just for writing those parts of the integral. Okay. All right, so now we're missing the other part. Since we have a wash here, we have this gaping hole in the middle. We're going to do the big one minus the small one. Okay? So let's do the big one. Now, again, same thing as before. Here's the axis of rotation right here. Which one is the farthest away from the axis of rotation? It is this function right here, which we already found out to be is x equals the square root of 9 minus y. So that is going to go first. That's square root of 9 minus y. Okay? Now, remember that we always do right minus left. Remember, we always do right minus left. So the rightmost function is right here. It's this one right here, right? So which one is to the left is negative 2. So we do right minus left. So it's this minus negative 2, which, again, what is this going to do? This is going to add to the radius. So that's 0 to 9, and this will be the square root of 9 minus y plus 2 squared. Okay? And so, again, it adds to the radius. Some people, there's two ways to do this. You can do right minus left whenever you're doing with respect to y, or some people just like to just look at it and just be like, okay, the radius was moved, and what did it do? It added 2 units, so they just put a plus 2 right here. That's another way. There's two ways to look at it, okay? And yeah, both of them still give you the same thing. So now let's go to the other one. Now I need the inner part. What's the radius of the inner part of that thing that we're cutting out? It is negative 2, right? Oh, by the way, if you want another, I guess, more mathematical reason for it, what is the rightmost function? It is 0. So if you do 0 minus, you do right minus left, so it's 0 minus 2, right? So 0 minus negative 2, or minus 2. And so you get this. It doesn't really matter. The negatives don't matter because if you recall, whenever you square something, it still turns out to be positive. So this will just be minus 4 whenever you're done doing this. So this whole thing will just turn out to be a minus 4. And then let's go ahead and let's start doing the math. So when you FOIL this and you do the math, you're going to get 9 minus y, right, plus that squared, that's 4. And then you're going to get plus 2 times a times b, which is 4 square root of 9 minus y. And then, of course, we have our little minus 4 right here. Okay? And hold on, give me a moment. Let's verify that this is mathematically correct. Yes, when you FOIL, this part will be blah, blah, blah. Yep. Okay. Oh, what do you know? Hey, look at this. Those cancel. Oh, that's nice. Okay, and so now we're just going to integrate all this leftover. Oh, by the way, I know you're probably thinking that this is like, I know it is, it's kind of tedious. If it makes you feel any better, in higher level calculus, one question could take up 1, 2, 3 pages, okay? So if it makes you feel any better, yeah, it gets a little bit longer, okay? All right, so let's do this. Pi, the integral of 0 to 9, and then this is 9 minus y plus 4 square root of 9 minus y dy. All right, and so when we integrate, we're going to get pi times 9y minus y squared over 2 plus 4, and who remembers how to integrate this? Let's see who remembers. I know it's been a while. How do you integrate that? How do you integrate that? Goes in once, goes in twice, right? If you remember, I hope you remember, we make u equal to 9 minus y, so du is going to be minus dy, so we need a negative. So there'll be a negative here, and then we multiply by a negative right here, so this will be negative 4. So negative 4, the integral, and excuse me, 0 to 9, and then this will be u to the 1/2 du. All right, and so when we integrate this, we'll get pi 9y minus y squared over 2 minus 4. U to the 1/2 plus 1 is going to give us u to the 3/2, which is just going to be 9 minus y to the 3/2 divided by 3/2, which is really just 2/3, right? And so we're going to evaluate this from 0 to 9, okay? And then, of course, we just plug in all of our variables. So this will be, all right, and so we plug everything in. We're going to get 81 minus 81/2 minus, and what do you know? When you plug in 9, this whole thing right here is just 0. But then when we do minus pi, we're going to get 0, 0. So we're going to get 0 minus 0 minus 4 times 9 minus 0, which is just 9, to the 3/2 times 2/3. So this will just be 81/2 times pi. And then this will be minus pi. And so here, let's do this. 2 times 4 is 8, and that gives us minus 8/3. That gives us minus 8/3. The square root of 9 is 3, and 3 to the 3rd. Right? Yes. Okay, so that's just going to be 3 squared. And so 3 squared, which is 9 times 8, is 72. So minus 72 pi. But then again, this negative times this negative turns into positive. And so whatever that thing is, oh wait, we can combine this. This gives us 71 pi, right, plus 81/2 pi. And then, of course, if you really want to combine like terms, multiply this out by 2, and that gives you 142 plus 81 all times pi plus 2 gives us 223 pi over 2. All right. I know, that was long. I know. It was long. But there you go. All right. Okay, there you go. All right, so now let's go on to another one. So that concludes, that whole process was just the first example. Okay, now let's go to the second example. All right, let's hope this might turn out to be a little bit easier. Okay, so it says find the volume of the solid formed by revolving the region bounded by the graphs of this equation, the quadratic equation, and about the line y equals 3. Okay, so here, let's take a look at this. Here's one, there's one. I'm going to draw a quadratic equation, and there we go. Okay, now you should definitely try to do this without a calculator, because some of the things that you guys are going to be required to graph is without a calculator. Okay, so you see this right here? All right, okay, it might be a little bit difficult to try to figure out what that thing looks like. Okay, you could just try to just make an XY table and just start plugging in random stuff, or let's do it the easier way. Let's find the zeros. Okay, if we factor out an x, we get 2 minus x equals 0. So we get x equals 0, and this one is going to give us x equals 2. So one of the zeros is at 0, and the other one is at 2. Now, what do I know? I know that a quadratic equation, it's even. They both go in the same direction. And so if these are the zeros, and they're both like this, let's see. What happens if I plug in 1? I'm just going to take a wild guess here. If I do this, I get 1. Oh, there's my other point. There it is. Okay, so it looks like this bounded region is right here. It's this thing right here. And then it says we're going to rotate about y equals 3. Okay, so here it is. There's the axis of rotation. And so bear with me. I'm going to rotate this. Okay. And so rotate this again. And so if we were to keep doing this, it would fill this in. And what do you know? We get this open part in the middle. It looks like a ring. It looks like a ring. Okay. And so we get that. Okay. Now notice that it's from, actually, you know what? I can go ahead and erase this. All right. So we're going to rotate about y equals 3. Now you notice that we rotated it like this, right? So where the rectangle is going to be, they're going to be right here. Okay. Now you notice this time they're not on the x-axis. Yes, I'm aware they're not on the x-axis, but the width, right, this dx right here, I don't know if you can see me shading this right here, right? Okay, would be the same as if it was sitting on the x-axis right here. Notice how they're kind of like parallel to each other, right? So that means that this integral is with respect to x. And so we put pi right here, right? Okay, what are the boundaries? Now remember, we're integrating with respect to x, so we need boundaries with respect to x. So what's the smallest boundary? 0. And where do they stop or intersect? At 1. Okay, and so now we need the big radius. Remember, it's the big shape minus the small one. Okay, now which one, again, is the farthest away? You want the one that is the farthest away from the axis of rotation. So, here, let's do it in yellow. The one that is the farthest away is that function right there. Which one is that one? Y equals x squared. So that's going to be my big one. Okay? Now, this is where it's very, very important what we did previously, okay, about finding the area between two equations. Remember that when we were trying to find the area bounded by two graphs with respect to x, we would always do top minus bottom. Do you remember? Okay. Well, okay, this is where this gets quite a few people is, which of these is the top equation? Which one is it? Well, guess what? It's actually y equals 3. Y equals 3 is the top equation. So that's 3 minus, what's the bottom one? X squared. And of course, remember we have to integrate area, and that's pi r squared. This is the big radius. So this is the big one, so that's squared. Now I need to do minus the little one, okay? So again, we're integrating with respect to dx, so we need top minus bottom. So what's the top equation? 3. And we're going to subtract the bottom one. What's the bottom one? Okay, and this is the smaller radius. The smaller radius is that graph right there. So if I erase this, it'll be 3 minus, parentheses, 2x minus x squared, squared dx. Okay? And that gives us a smaller inner part. Okay? So all we have to do now is just do some basic algebra. Okay? Like I mentioned before, you're going to get credit just for setting up the integral, because that's the crucial part. Because after all, if you do come across this on the calculated portion, all you'd have to do after this is just plug it in. Okay? All right, so let's go ahead and let's do the math here. This will be x to the fourth. This will be minus 2 times a times b, which is going to give us 6x squared plus 9 minus, that's going to look ugly. Okay, so that's going to be, what is that? Minus minus is a positive x squared minus 2x plus 3. Oh, wow. That thing's going to be a mess. Okay, because we're going to have to square this, and we're going to get this gigantic polynomial. So you know what? I guess it's safe to say that, okay, this may be a calculated portion of the exam. Okay, hold on one sec. So you know what? I don't think that you'll be required to do something this complex, but just in case, all right, if you want to see it, you would plug this in the calculator if it was on your calculator portion, but if you still want to see what it would look like, you would basically be doing this. And you're going to do minus, and you're going to foil that gigantic thing right there. Or more accurately, you're going to distribute, okay? Which is, and that would be blah, 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 blah. That thing right there. Okay, and here, let's just verify that this is on the right track. So, boom, 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 that's okay, and yep, that's it. Okay, so you basically plug this whole thing in here. So you get x to the fourth, and where are my cubes at? Here they are, here they are. That's minus 4x cubed, so there's that. Okay, where are my squared terms at? What is this thing supposed to be? That's supposed to be a plus 4x squared. So that would be 3, 4x squared, so that's going to give us 4, 7, 10. 10x squared, and that takes care of this, minus 12x, and finally plus 9. All right, and then of course, don't forget that that negative flips everything. Combine all your like terms, and then finally integrate. Oh, what do you know? This is nice. This cancels right here. That cancels. All right, we get negative 6x squared. Negative 6x squared minus 10x squared. That's going to be a minus 16x squared. Well, hold on. First, before I do that, let me at least put this in descending order. Boom, 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 boom. Okay, there we go. That takes care of this. Okay, what else we got here? We got a negative 12x, so that's going to turn into positive 12x. And 9 minus 9s, they cancel. Oh, what do you know? Look at that. That turns out to be kind of nice. Oh, and so we integrate this, and we're going to get minus 4x to the fourth over 4, etc., etc. Blah, 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 blah. Oh, wow, this is even better than I thought because we're going to evaluate just from 0 to 1. So this really just gives us pi times these fours cancel, so that's just going to give us negative 1. And that's going to just give us minus 16 over 3. This is 12 divided by 2, which is just 6, so that's just going to be a plus 6. And of course, minus 0. And let's see what else we got here. 6 minus 1, that gives us 5. So that's 5, this, blah, 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 blah. And let's see what else we got here. This. And so... You know what? Now would be a good time to just check to see. Let's verify this. Let's go back here to the top. Okay, so my apologies, you guys. I made a small sign error right here. This should be, whoa. This right here should be positive, because a negative times a negative from above gives you positive 4x cubed, which then in turn makes this positive 1, and then that changes this to 7, and so when we do that, that gives us 7 times 3 is 21, and then, okay, what is that? 5/3 pi. And there you go. So the volume of this entire shape is 5/3 pi. Hey, by the way, a way to check is that you notice that earlier I got something negative. That's how I knew that I made some kind of mathematical error because, yeah, you can't have negative volume unless you want to start talking about antimatter and other kinds of stuff like that, like advanced concepts. But anyways, okay, we're just going to stop right there. All right, and so that concludes this lesson. All right. Now, I'm going to leave this ticket out blank, and you notice that this starts a shell method, which is next week. You also notice that there is no other day, like second day of the disc and washer method. Okay, normally the reason I do that is because I just give students another day to just work on their homework or any questions they can in class. All right, so you basically get like an extra day to just work together in groups. There's something else I also wanted to bring up. Since these are going to be posted to YouTube, but you guys know that you guys can post comments, right? So just want to let you know that you can post comments. I hope that they're constructive mathematical questions, right? And then, of course, if other people are watching them, then you guys can kind of work together as a team, all right? All right, so good luck. Good luck on your test this Friday. All right, like I said, I apologize I haven't been able to be here, but all right, we're just going to have to be able to make do. One other comment I also want to make is that on my whiteboard when you guys come to class is the schedule for the after-school practice AP exam. Okay, so there it is. You guys have it about a month in advance, so you guys can pick which day it is you want to. All right. Obviously, if you pick the one for Maid Creek, then you guys would just stay here after school and just take it right here. Okay. All right. Good luck to everybody. Have a good one. Hoorah.